So today we're going to look at two different views of statistics, the classical or the frequentist and the Bayesian point of view of statistics. So what I'm going to do is just contrast classical, frequentist, and Bayesian statistics, and then I want to go through some examples, um, first comparing classical and Bayesian statistics, and then some examples, other examples of Bayesian statistics. So first of all, there's different views of what probability is. From the frequentist standpoint, probability is the relative frequency of an observed outcome relative to other possible outcomes. From the Bayesian perspective, probability is a measure of the strength of belief regarding the true situation. There's a difference in reasoning. The frequentists are deductive. Bayesians are inductive. That is, the sample is what we have, so the true situation might be this. In other words, you're going to look at the differences in what is random. For frequentists, the population parameters that we're wanting to estimate, like a mean or a regression coefficient, are fixed. The observed data is random. From the Bayesian perspective, however, the data is fixed and the population parameters are random. That's a really important difference to keep in mind. So they use frequency distributions differently. From the frequentist standpoint, the distribution gives the probability of getting a different outcome given certain parameters. But from the Bayesian perspective, frequency distributions give the probability of parameters with different values given the observed data. Also, they use prior knowledge differently. From the frequentist standpoint, conclusions from a set of data are based only on that data. However, from the Bayesian perspective, new observations can add to our information about our population. So if you have in Bayesian terminology, what we have a prior belief about the population, then this can be updated if we get new observations. What they never say, frequentists will never say that probability is that a statement is true. In other words, the null hypothesis true, the alternative hypothesis true, the probability that the true value lies within some interval. On the other hand, Bayesians will never say, or they'll never talk about p-values. They'll never use the term significant. They'll never say the null hypothesis is, or the confidence interval is. So we'll give some examples of this later on. So in terms of contrasting the two approaches, from the classical standpoint, a p-value is the probability of getting a result as extreme as what we observed, and it's assuming that the null hypothesis is true. That is, the hypothesis that there is no difference in the population. The Bayesian approach, however, uses probability statements that are directly related to the null and alternative hypotheses. In other words, how likely is a particular value of the parameter given the data? Then remember again that and from the Bayesian perspective, the data is what's fixed. The parameters you're estimating are random. Classical is just the opposite. The parameter is fixed, the data is random. So let me sort of give a picture here, representation of the frequentist view of hypothesis testing. And so in the population, which we'll represent here by the large circle, there is a mean, a population mean. And from the frequentist standpoint, that is fixed, but we don't know what it is. So we draw a research sample to estimate this population mean. And so from a theoretical standpoint, we could draw multiple random samples, in fact, an infinite number of random samples from the population. And it turns out that the mean of the means of these random samples will equal the population mean. So let me give you an example here of diastolic blood pressures. I have 144 here. It's a small, but we'll call it our population. And so from a frequentist standpoint, what we're going to do is we're going to draw random samples from this population of blood pressure values. And so we're going to draw them with size 5. And we could, keep going here. But basically what we get then is what we call a sampling distribution. So when we talk about a sampling distribution, we're talking about a distribution of statistics, in this case, the mean. So we have a number of random samples that we've drawn here and calculated the mean, and then we can order the mean from the lowest to the highest, and this is our sampling distribution. And so when we talk about estimating the mean, we can calculate what's called a 95% confidence interval, or we could do a 90% confidence interval, but 95% is typically the one that's calculated. And from our samples of size 5, then we can compute the interval, the lower bound and the upper bound of an interval. And so from the frequentist standpoint, or the classical standpoint, what this means is that 95 times out of 100, or 95% of the time, the interval will include the true population mean, okay? But 5 times out of 100, or 5% of the time, it won't. And you can see here, even in my small example, there's a couple of instances here where the population parameter falls outside the 95% confidence interval. So that's from the classical or the frequentist perspective, that what it means is over repeated sampling, the confidence interval will include the true population mean 95% of the time. So when we do hypothesis testing from the frequentist standpoint, we have the null hypothesis, which we're going to assume that's true. And so what that means is that whatever difference we observe between the means of, say, a treatment and control group occurred by random sampling variability or chance. The alternative hypothesis is that there is a difference between the means that was unlikely to have occurred just by chance. So as say in the classical standpoint, statistics, we assume the null hypothesis is true. Then we do our statistical test, and then we're going to either reject the null hypothesis or we're going to fail to reject the null hypothesis. From the classical standpoint, you never say we accept the null hypothesis or we accept the alternative hypothesis. You either reject or you fail to reject the null hypothesis. So in calculating our test statistic here, which is in this case just going to be a simple t-test, which is the difference in means divided by the standard error of the difference, and then the t-distribution that we use, which is looks like a normal distribution, but each t-distribution depends on the sample size. And in your textbooks or where you look at to understand a t test, uh, it's defined by its degrees of freedom. And degrees of freedom, means that that's the number of components of a statistic are free to vary. And I just have a quick example of that. So say we have three numbers and we know that they all add up to 100. So in terms of what these three numbers are, say we say the first one is 50, then that means that the second and third numbers can still be any number. In other words, x2 and x3 are free to vary. But if we assign 40 to the second number, then the third number is fixed. It can't vary. It can only be, in this case, 10. And that's what we mean by degrees of freedom. So when we calculate a t-test, this basically the numbers here that I have in my example, the difference in means divided by the standard error of the difference in means. And so we come out with a t-value of minus 1.4. And then in the t-distribution with 8 degrees of freedom, then the p-value for that is 0.09. And so if we were to do a two-sided test, then the p-value would be 2 times 0.09 or 0.19. And so in this case, in terms of our example that we had, we would fail to reject the null hypothesis at the 0.05 level. We looked at our p-value, which is typically set at a significant, what is termed a significant p-value, is set at 0.05. So in this case, we'd have to reject, fail to reject the null hypothesis. And so what conclusions can we make? Can we say that there is no difference between treatment and control? The treatment does not lower heart rate? Well, no, we can't make that conclusion. And why can't we? Because all we can say is that there's no evidence for a treatment effect. From the classical standpoint, we never know what, even though there's a true value out there, we don't know what it is. So our conclusion would have to be there's no evidence for a treatment effect. On the other hand, if the null hypothesis is rejected, then we can't say that the treatment lowers heart rate. We'd have to say that there is evidence that the treatment lowers rate. Technically speaking, now obviously in use in published papers, they say that treatment lowers the heart rate. But technically what we have to say is that we have evidence that the treatment lowers heart rate. So I want to give an example here of doing a t-test from the Bayesian perspective and then from the classical perspective. And so this is looking at NT-proBNP. BNP is a beta type peptide. I don't remember exactly what all that stands for, but anyway, it's a marker, biomarker for heart disease. And so remember that from the Bayesian perspective, we have to assume a prior distribution. And so in this case, we're going to assume a normal distribution with a mean of 0 and a variance of 0.01, or the variance then would be the standard or the square root of sigma 2. And so here's the results from running this from the Bayesian perspective. And let's see, let me get myself out of the way here. I can. So what we're going to do then is we're going to sample repeatedly from this normal distribution that we've assumed. And we're going to do, when you do Bayesian analysis, we do what's called Monte Carlo Monte Carlo Markov chain uh, um, sampling. And so we have to do a certain amount of burn-in just to make sure we don't get a weird value. So our Monte Carlo Markov chain sample size is going to be 10,000. So we're going to make 10,000 random draws from this normal distribution. And the actual number of observations that we have in our data is about 2,650. But remember that we're not drawing from the observations themselves. We're drawing from a prior distribution with a mean of 0. Okay, and so here's what we get. And so remember, we're comparing males and females. So in this case, if the patient is male, it's coded 1. If it's female, it's coded 0. So here's our constant 710, and the regression parameter for males is a minus 264. Okay, so that means that if the patient is male, then we subtract 264 from the 710, we get 446. If the patient is female, then it's the constant 710 times minus 260 or plus or minus 264 times 0. So in other words, if it's female, the BNP value is 710. But for the regression from a parameter for males, over here we have an interval of minus 337 or minus 338 to 190, minus 190. And we call this in the Bayesian framework a credible intervals. Okay, and we're going to contrast that with a confidence interval from the classical perspective. So notice that, whoops, let me go back here. Notice here that we have no p-value when we do Bayesian analysis, okay? But when we do this from the classical standpoint, notice that here's where we have our p-value. So it's a very small p-value. And so in this case, we would reject the null hypothesis that there's no difference. But notice the coefficients here, minus 401 and for males. So that means that if the patient is male, we're going to subtract 401 from 843, gives us 432. And now our interval here, we call a confidence interval. And so what we need to remember is that these have different meanings depending on the interval has different meanings depending on your perspective. So from the Bayesian perspective, we have a credible interval. And what that means is that there's a 95% probability that the interval includes the population parameter. So it was minus 337 to a minus 190. From the frequentist standpoint, the 95% confidence interval means that over repeated sampling, the interval will include the population parameter 95% of the time, okay? And so notice that we get different numbers here that have different meanings. So here we're 95% confident that this interval here contains the true population parameter. Here, there's a 95% 95% of the time, this interval will include the true population parameter. Okay, and so this is probably one of the most important things to remember especially when you read literature, the difference between the Bayesian credible interval and the frequentist confidence interval. Okay, so and this is the distribution for males and females of BNP. And you can see that it's extremely right skewed. So most of the values for both are down are relatively small, but we have some extreme values that approach 30,000. In fact, as I remember, I think the smallest value, which for either one is like 5 or 6, but there are values out here in the 20,000 range, and one that I think is 29,000. So it's extremely, the actual distribution is extremely right skewed. Okay. So let's do another comparison here for left ventricular mass. Again, this is used as a marker for heart disease. And so we're going to start out with the same assumptions. We're going to compare males and females. And from the Bayesian perspective, we're going to assume a normal distribution with a mean of 0 and variance of 0.01. And so we're going to do the same thing. We're going to draw a Monte Carlo Markov chain 10,000 times. And the results we get, we can see here that we get a mean for males, the regression parameter, not a mean for males, but a regression parameter for males of 43. Our constant term is 142. So what that means is that if it's male, it's 142 plus 43. If the patient is female, it's just 142. And so here is the 95% credible interval of 38 to 48 for this regression parameter for males. Okay, then from the classical standpoint, again, we have our p-values. Notice the numbers that we get in this case. The regression coefficient for males is 43. The constant term is 143. So again, it's for males, the left ventricular mass would be 142 plus 43. The confidence interval for males is 38 to essentially 48. And if you remember our previous slide, then we see that the intervals, whether it's the Bayesian credible interval or the frequentist confidence interval, are virtually identical. And so they say, well, how did that happen? Well, we'll just say it happens. So you can get different answers depending whether you do the Bayesian or frequentist from perspective, as we saw in the previous example with BNP, but we might get the same answer either one, but doing either Bayesian or frequentist the same in terms of the number. But remember, these, even though the numbers are the same, they have a different interpretation. So from the Bayesian perspective, this means this interval, we're 95% certain that the population parameter, the male regression parameter, falls in this interval. From the frequentist, this means that if we were to sample over and over again an infinite number of times, this interval would include the true population parameter 95% of the time. Okay, and so if we look at the distributions between males and females of left ventricular mass, then we see that they're pretty much the same. Obviously, there's more males in this example than females, but the distribution is pretty much the same, and that we have less extreme values, or the extreme values are smaller than they were for B and P. So that may play into why these came out the same in terms of the numbers of the in the lower and upper bounds of the intervals. Okay, so that gives you kind of a perspective of the difference between classical and Bayesian perspective. What I want to do then is go through some examples where Bayesian perspective is commonly used. And the one that most probably clinicians or epidemiologists would be familiar with is the use of Bayes' theorem of conditional probability, the probability of event A given event B. So this is the formula for Bayes' theorem. As probably most everyone knows, Bayes was an English statistician and actually a minister that developed this formula. And so the application is usually applied to diagnostic tests. And this is what, again, most clinicians or epidemiologists will be familiar with. So we have a test for a particular disease, and then we have whether the test is positive or negative, and then we have whether the disease is actually present or the disease is not present. And so if we look at the test being positive and the person actually having then the disease, sensitivity is defined by the true positive divided by the true positive plus the false negatives. On the other hand, if the test is negative and the person doesn't have the disease, then our term here is what we call specificity, which is true negatives divided by true negatives plus false positive. The values that are particularly of interest are the positive predictive values and the negative predictive values. So a positive predictive value means that if the test is positive, what is the probability that the person actually has the disease? And so that value is the true positive plus the false positive, or is the true positive divided by the sum of the true positive and the false positive. The negative predictive value is then the true negatives divided by the true negatives plus the false negatives. And that gives us the negative predictive value. So in words, then the sensitivity is a proportion of true positives correctly identified by the test. Positive predictive value is the proportion of patients with a positive test that actually have the disease. And specificity is just the opposite of those. So what we may not know, or what may be different in different populations, is the prevalence of the disease. And sensitivity and specificity of a test are independent of prevalence. However, the predictive values, both positive and negative, are dependent on the prevalence. And so what we're going to do is we're going to use Bayes' theorem to estimate the predictive values given different prevalences. And so here's our Bayes formula for predicting the disease with a positive test. Our prior probability then is the prevalence of the disease in the population. And our posterior probabilities are going to be our positive predictive value and one minus the negative predictive value are going to be our revised estimates of the prior, the prevalence of the disease. So I've given here the formulas. I'm not going to go through these in any detail. You'll have the slides to look at this, and you can find these in any textbook. But what we can do then is, given a particular prevalence, we can then recalculate the predictive values, both the positive predictive value and the negative predictive value. Okay. So an example here, where I have abnormal and normal, or with some pathology. And so I put in actual numbers here. So our sensitivity is just 231 divided by the sum of those that have a positive and negative, both a positive and a negative test that are actually abnormal, 258, which comes out to be nearly 0.9. Specificity, the number of negative tests that are actually negative, that are normal, is then 54 divided by 86, the sum of 32 and 54. Our predictive value is, remember, that's those that have a positive test, the probability that they actually are abnormal. So that's 231 divided by 263. Our negative predictive value is 54 divided by 81. It turns out that the prevalence in here, in my example here, is 75%. That's the abnormals divided by the total numbers. So that's 258 divided by 344. So in this case, we have a fairly high prevalence in the population. Well, what if we encounter a population where the prevalence is only 50%? Well, with that, we can recalculate the positive predictive value with Bayes' formula. And so we have our predictive value divided or times 0.5, the actual prevalence in our population that we're interested in. And so carrying the formula out, we get a positive predictive value of only 70%. If we want to, say, calculate for a prevalence of 25%, then the positive predictive value is even lower. So you can see that depending on the prevalence in the particular population, that the predictive values, the positive predictive values decrease. So a next example then was from a published trial that looked at 3 medications for epilepsy. And so what they did, I know this is sort of hard to see here, but I have here pretty much the methods and the statistics for the study that was done in comparing these 3 anticonvulsive agents for epilepsy. And so it's a randomized trial. It's blinded. Adaptive means that we're going to recalculate the sample size needed as we go along. We're going to then also develop stopping rules. That means that we can stop the trial if we have evidence that the treatment works, or we can stop it if it doesn't, if the treatments don't work. And so what they're going to do is calculate, they're going to make an assumption about the prior probabilities and then update these to the posterior probabilities that each drug was the most or least effective. And so their primary outcome was the absence of clinically apparent seizures. So that's just yes or no. And then they're also going to look at safety outcome, was a composite of several different components here. But we're going to look at the primary outcome. So, as I mentioned, they used a response adaptive comparative effectiveness design. And so to begin with, patients were randomly assigned to receive one of the three trial drugs initially in equal ratios. So you start out with equal numbers in each group. But after 300 patients were assigned to a treatment group, so you have 100 in each group, then their adaptive scheme comes into play, where now the randomization is going to be based on the updating the prior probabilities. And then, as I mentioned, they're going to do interim analyses where at different sample sizes at which time the trial can be stopped. So the important thing here is that randomization was stratified according to age. And here's their prior assumption. They're going to assume that all three drugs will be equally the most effective or the least effective. In other words, there's in the terms that we commonly use with the frequentist notion, there's going to be no difference. So here is their Bayesian analysis, where they're going to start out with assuming that the distribution is uniform. In other words, uniform is, well, you can have different numbers here, but they're going to assume a uniform value of 0 to 1. And then this is going to be updated on the basis of their analysis, and they're going to use a binomial or beta binomial distribution to model the posterior distributions. So the uniform distribution here is what we call a non-informative prior. In other words, we're going to assume that they're all equal. Oops. So they did 10 to the 6th iterations and calculated the probability that a given treatment was better than the other two. And so their decision here is based on that it was most effective or least effective with a probability greater than 0.975. And then they see here that they're kind of reverting back to the conventional frequentist. The 0.975 was analogous to an alpha of 0.025 in a one-sided comparison. So this is the Markov chain Monte Carlo iterations here, 10 to the 6th, the number that they're going to do. And so what they come up with is a cutoff for if a response of 65% was true in one group and 50% in the other groups. In other words, if there was 15 percentage points difference, then they're going to assume that one is better than the other or one is better than both. And so their statistic that they're going to calculate are 95% credible intervals. Okay. So that's the Bayesian analysis for this particular study. So here are their results. And so I underline no significant difference because that's something that Bayesians are supposed to never say, but you can see they're kind of vacillating here between the frequentist and the Bayesian. But anyway, from the Bayesian's perspective, they find no difference. And you can see they've graphed the distributions here. It's a little hard to see, but these are the 95% credible intervals that they calculated from their Monte Carlo simulations. And so you can see that they're virtually overlap. And when they graph the distributions, get histograms here, you can see that they're virtually on top of one another. So their conclusion would be that there's no one treatment is not any more or less effective than the others. So what would this histogram look like if there had been a difference? Well, this is what it would look like, that you'd have one treatment here, and so there'd only be a 2.5% overlap in the distributions with one with the other if it was better or worse, depending on which way the analysis went. Okay, so again, I repeat this because this is the important thing one of the important things to take away, that the Bayesian confidence interval is a credible interval, and it means that we have a 95% probability that the interval includes the true population parameter. But the frequentist interval, the confidence interval, has to do with repeated sampling from the population. Okay, I want to then finish up in terms of examples here with what's called probabilistic Bayesian sensitivity analysis. I'm going to do this because this is a common way, well, maybe not common, but it's becoming more used in situations where you have multiple input variables to estimate multiple parameters. And because parameter estimation is sensitive to change in input variables, the Bayesian sensitivity analysis gives us an idea of how whether, or it gives us a probability of the distribution of our outcome. So the difference here is that the prior and the posterior distributions in the probabilistic sensitivity analysis are the same. So we're not changing the posterior distribution from the prior. So it's going to be either normal or gamma or beta or some other distribution. The thing is, though, in probabilistic and sensitivity analysis, we can have different distributions for different variables. So I'm going to give an example that we did some time ago of cost-effective analysis. And this is one area where the probabilistic sensitivity analysis is really useful. And so we're going to compare the cost and effectiveness of two treatments, or maybe more. And we have both patient-level costs and patient-level measures of effectiveness. And so in cost-effective analysis, we need an outcome, which is survival, and we use life years gained, or more often is what we call quality-adjusted life years. And so qualities are calculated by multiplying the life years by a utility, a measure of health status. And there are different instruments that measure this, but they're all scaled from 0 to 1, 1 being perfect health. And for cost, there's different things that you may or should take into account: costs of procedures, physician cost, medication costs, hospitalization, and so on. And so this is just an example from our study that we did. We looked at the different costs, but I just give a couple here for a fatal cardiovascular event, a death, for 3 different age groups, and then a cost for the same different age groups for non-fatal MI. And so you can see that we have a mean standard deviation, but all of these are gamma distributed. In other words, we're going to use a gamma distribution for each of these. And the gamma distribution, they're going to be different gamma distributions depending on the mean and standard deviation here. And then also what you have to do in cost-effective analysis, you have to justify or come up with these costs. And so we have references that we use to come up with these costs. Cost is always right skewed. And actually there's no transformation you can do to make it normally distributed, but you can visualize this, that you can see that you have most of the costs for some particular disease or whatever here, but there are always, the outliers here. And so this is right skewed. So that's why we're modeling cost as a gamma distribution. For the utility values, we're going to use a beta distribution that's between beta distribution between 0 and 1. So if a person has no history of cardiovascular disease, then that value is 1. So if we multiply their quality adjusted life years by 1, we get the same value. However, if they have a history of, say, angina or myocardial infarction, stroke, so on, then their quality of life decreases. Is decreased by this particular factor. And you can see again that we have references to justify this. The disutility here indicates if they have one of these during the trial, remember this is history up here, but if they have one of these during the trial, then we subtract this amount from their quality adjusted life years. And again, that's coming from the literature that deals with the costs of things. So, and that's one thing about cost-effective analysis. You have to be very specific what you're basing your costs on or where your estimates are coming from. So here is a picture I'm trying to draw a very simplistic idea of what we do when we do probabilistic sensitivity analysis, is that we're going to draw not from the actual population, but we're going to make random draws from the theoretical distribution. So here's the cost, a gamma distribution for a fatal cardiovascular event, non-fatal MI, non-fatal stroke. And here's a distribution if they're taking atorvastatin. And then over here is our beta distributions for our quality of life, if they have a history of MI, history of stroke, and so on. And so we're going to do 100,000 random draws to come up with a distribution of the cost effectiveness. And that's going to be for the 100,000 random draws that we make, the mean cost divided by the mean quality adjusted life years. And so I've shown here like one draw we might make by the solid line. So here this is a patient, a theoretical patient that has a stroke. So here's the cost of a stroke. And this person has a history of angina, and they're taking atorvastatin. So we would draw from these three distributions. And so that's why we do a lot of random draws here, because we're drawing from a number, sometimes a large number, of theoretical distributions. So again, to summarize here, from the frequentist standpoint, probability is the long-run frequency of random events over repeated sampling. The data are random. The population parameter, like a mean or regression coefficient, is fixed. From the Bayesian perspective, probability is an index of confidence an investigator has about the occurrence of the event. And from the Bayesian perspective, data are fixed. The population parameter is random. So a few comments I want to make here in summary. Frequentist methods are typically used for simpler, straightforward analyses. So if you're doing just a t-test or an analysis of variance, where the Bayesian methods are really useful is if you have complex multi-parameter analyses. And these are usually difficult for frequentist methods. Frequentist methods can handle change in one or two parameters at a time, but not multiple parameters. And in Bayesian simulation, sometimes you can see that the first iterations, a large number, are for burn-in. That's so we don't get an odd result right off the bat. In the examples I used, we did 2,500, which is usually sufficient, but they can be more. So Bayesian analysis, you have a prior belief, you get new information, and then you revise your prior belief with your posterior belief, your new belief. And so I have an example here of physicians that's particularly applicable to physicians or clinicians. Clinicians usually do their analyses if they're publishing papers from the frequentist perspective, because that's probably what they've been taught in medical school. However, in practice, they are really Bayesians because you get new information, you see a patient, the patient has initial medications that they've been taking, and then the physician may update those medications based on current lab results, may increase or decrease the dose or whatever. So in practice, clinicians are essentially Bayesians. So the advantage of a Bayesian approach in clinical trials, first of all, it allows evidence to be used. In other words, you can have sequential learning. You can use historical data. You can use similar trials or similar groups that have the same disease. And it does allow direct probability statements. So you can say, what is the probability that my drug is better than placebo, for example. So you're calculating a probability statement that's relevant to the that applies directly to the null hypothesis or to the alternative hypothesis. The disadvantages are that is the choice of the prior as probably the primary one, because you typically don't know what the distribution is. You're going to make some assumption for your prior, and it may be that you'll get lack of consensus on an appropriate choice of prior. A lot of times you'll see when you come across a Bayesian study is that they use what's called a non-informative prior, but there can be problems with that as well. And you need pretty large sample sizes for understanding like the safety of a drug or its impact on the numbers of patient exposures prior to the registration. And the statement still holds that independent replication of results is still the strongest evidence of an effect. So just in summary, frequentist that's based on repeated sampling of data from a population. The confidence interval is related to repeated sampling, and that you get a confidence interval 90, 95%, 99%, whichever you want to do. That refers to the interval, including the population parameter, X percent of the time, 95% usually. Bayesian, we have a prior distribution, an assumption that we make. We then look at the data and we come up with a posterior distribution. And we calculate a credible interval, not a confidence interval. And that's the key point here, is to remember the difference between the two. So the credible interval is the probability that the interval includes the true population parameter. A couple of things that are relevant to both is the sample really needs to be representative of the population. In either case, if the sample is not representative of the population, then your results are not going to be valid in either case. And in both cases, whatever interval you're talking about, a confidence interval or a credible interval, the smaller it is, then the more accurate your estimates, whether it's over repeated sampling or the probability, or the smaller the CI, then even if you're calculating a 95% credible interval, then the smaller that is, the better your estimate. So I just have one reference here, although it's written in the context of econometrics. The first chapter, probably two, go over sort of the essentials of Bayesian analysis, and they contrast it with the frequentist analysis as well. It's a little more technical than you might like, but I think it still is fairly readable. But it gives you, particularly the first few chapters, give you a good understanding of Bayesian analysis. Okay, so I'm almost out of time. I thank you for your participation. If you have any questions, you can email those to me. Let's see if I can. Okay, the question you have is either way, isn't probability based on repeated sampling? Yes, it is in a sense. The frequentist is based on sampling of the actual data. Okay, in other words, your sample that you drew from the population, you do the analysis based on the actual data. From a Bayesian perspective, you're drawing from theoretical distributions. Okay, now the distributions are based on the data, but you're not drawing directly from the data. You're drawing from theoretical distributions, whether it be a normal distribution or a gamma distribution. And that's the difference. Okay, well, it's the top of the hour, so I'll stop there. If there's any other questions that you have, please email me at my MedStar address. Again, thank you for your time and attention.